Okay, this is calculating average atomic mass, worksheet 1, and this will be numbers 1 through 3. So the first thing is, on the question, copper is made of 2 isotopes. So isotopes are just copper atoms that have different numbers of neutrons, which could make them heavier or lighter. So your first isotope is copper 63. This notation, where you have the name of the element, a dash, and then the 63, this number is what is called the mass number, which is the number of protons plus neutrons. Sometimes you'll hear people call it the atomic mass. That's not technically correct, but I'm also going to put a video on here to explain some of that here in a little bit. So that's the copper 63, and then this is its percent abundance. Percent abundance just means if I dig up some copper and I actually looked at all the individual copper atoms, and if the copper atom had a mass of 63, I sat it to the left, and if a copper atom had, like you see here, the copper 65, I sat it to the right. Then when I got done, I'd have a pile of copper 63s and a pile of copper 65s from the copper I dug up. And if I looked at the percentage of each, I would have 69% copper 63 atoms, and the other 30 or almost 31% would be copper 65 atoms. So that is percent abundance. Okay. And so what we're going to do here then is we're going to take the actual mass of that copper 63 atom, which is the true atomic mass. But again, if you're interested, there's basically 3 terms here that are kind of confusing. It's not going to be a problem for you on your test or anything, but if you want to sort out the difference between mass number, atomic mass, and weighted atomic mass, or sometimes what's just called atomic weight, I'll put a video on the stream that'll sort that out for you. Okay, but anyway, so this copper 63 has an actual mass of 62.9296 AMU. And that's another thing you need to know. AMU stands for atomic mass unit. And it is just like pounds for us when we weigh on the scale. It's just the unit that we use to measure individual atoms, right? They're freaking tiny, so they have to have their own unit, and that is the name of that unit. All right, so that's a lot of background. To calculate the weighted average atomic mass of this, though, which is what you'll have to do in your test, this is really simple. All you have to do is take the mass, so in this case the 62.9296, so 62.9296, and multiply it by its percent abundance, which is 69.17. Now, just keep in mind, you're going to multiply it as a decimal. So 69.17% will actually be multiplied by 0.6917. This is the reverse of what you do in your calculator when you're calculating your grade. So say you're calculating your grade on your test and you got 7 out of 10. If you punch that into your calculator, 7 divided by 10, you get 0.7. But you know that's actually 70%. So this is just that in reverse. So we shift the decimal point 2 to the left, and you get 0.6917. You multiply that in your calculator, and you get a result of 43.53. And then the reason I use 4 numbers, and it won't matter if you use more or less, I won't ever count off for that, but I just use the smaller number of numbers that are in the numbers that I'm multiplying by. And then I'm multiplying that by 64.9278, which is the mass of the copper 65. And I multiply that by the percent abundance as a decimal of the copper 65, which is 0.3083, and that gives me a number 20.02, And then all you have to do once you've done that is add those together, and that is your atomic mass, or weighted atomic mass, and it ends up being 63.55 AMU. And make sure you include your unit in your answers, or you will lose points on tests. And that's how you do it. So on to the next one. Okay, this one introduces, and this whole worksheet does this because I'm trying to introduce you to different things here. So chlorine that is put into a pool is made of two isotopes. Again, just chlorine atoms that have different amounts of neutrons in them. And see here you have this new symbol. This is what's called isotope notation. So isotope notation looks like this. It has the chemical symbol, and then it has a small number up top, and oftentimes you'll see it with a small number down on the bottom. So in this case, if it did have the bottom number, it would be 17, which is the atomic number of chlorine. But anyway, this is just a way to represent the atom, the isotope of that atom, showing its mass number and its atomic number. Again, sometimes you'll see it without the atomic number down here because we can figure out the atomic number from the chemical symbol. Okay, so that is isotope notation, and you'll need to be able to interpret it. So you need to know the big number is your mass number and the bottom number is your atomic number. And then this problem works the same. So we're going to take the mass of chlorine 35, which is 34.969, and we're going to multiply that by its percent abundance as a decimal. So 75.53, if you shift the decimal 2 to the left, is 0.7553. Multiply those together, you get 26.41. And then our other isotope is chlorine 37, and it has a mass of 36.966. Multiply it by its percent abundance, which is 24%, or 24.47%, and shift that into a decimal. So 2 to the left makes it 0.2447, and that gives us an answer of 9.046. Again, I'm just putting this smaller number of numbers into my answers to match what was in the problem. Doesn't matter if you do that, you won't lose points if you don't. And I add that together and I get 35.46. And don't forget your unit, AMU. And that is your weighted average atomic mass for the chlorine. Okay. Then on to 3. Now 3 is not a problem. 3 is just asking you if you understand what a weighted atomic mass represents. So what we need to look at here is a number line between 6. So this is 6. And this is 7. And you would have 6.1, right? And 6.2, 3, 4, and then 5, so 6.5, and 6.6, 6.7, 8, 9. Looks like it went a little long. I'll make that 7. Ignore that part of the number line. 7. So this is our 6.9. So again, what happens when you look at the average atomic mass or weighted atomic mass, which they give you for it, which is what you were calculating in the first two, it's 6.941 AMU. That would be right in here. So this is where the 6.41 would land on the number line. If you just average these two, right, isotopes together, 6 and 7, you would get 6.5. So you would think the average would be right here. But remember, this is a weighted average. It takes into account how much of each one you have. So if you were doing the math we did before, we must have had a lot more of the lithium-7 than the lithium-6 to shift the average way over here to 6.9, and that's the case. So the answer to this is simply lithium-7 is more common. But the answer is it's more common because the weighted atomic mass is closer to 7 than 6, which means there must have been more lithium-7 than lithium-6 in the natural sample that was digging up and analyzed. Okay, that is that. So I will conclude this video.